And welcome to the YouTube channel D Creations Resources. We are looking at different aspects from physics, maths, etc. So today let us talk about a topic which is of course part of mathematics but very important for physics and engineering as well, because a lot of physical systems can be described or studied using it, and so it's always taught in mathematical methods of physics. So the topic is Fourier analysis, which basically involves Fourier series as well as Fourier transforms. So consider a signal, and if that signal can be written as a sum of sinusoidal components, that means the simplest periodic signals, we are basically talking about a Fourier series. So, Fourier analysis has been developed from employing sines and cosines to model periodic physical phenomena. Now, this periodic term is very important. Rather than just talking about some signal, let us try to relate it to music, which everyone loves. So, if you borrow from the musical terminology, every pure tone are single sinusoids. They can be called as harmonics, and the complicated tones are sums of harmonics. So, we will associate a periodic signal with a discrete set of frequencies, its spectrum, and the amount that each harmonic contributes to the total signal. So, if we know the spectrum and the amount that each harmonic is contributing, then we know the signal, and similarly, vice versa. So, we can analyze the signal into its component parts and we synthesize the signal from its component parts. Now, this idea can be extended to non periodic phenomena via the Fourier transform. So, in other words, we can say that we can get from a Fourier series to the Fourier transform by considering non periodic phenomena as a limiting case of periodic phenomena where the period is tending to infinity. So basically, the Fourier transform arose as a way of analyzing and synthesizing non periodic signals, and the spectrum that we had mentioned earlier becomes a continuum of frequencies rather than a discrete set. Now, usually a signal which will be varying with respect to time is in the time domain, and its Fourier transform is going to give you a function depending on the spectrum. Thus, it is representation of the frequency domain. So, from time domain, you are going via Fourier transform to frequency domain. So, there is this transformation associated. So, in other words, we can say that a Fourier transform is a mathematical model which helps to transform the signals between two different domains, such as transforming signal from frequency domain to time domain or from time domain to frequency domain. Now you might say that fine, this is a mathematical model, but what does it have to do with spectroscopy? So let us try to connect these two as well. So as you know that in spectroscopy we are considering the interaction of electromagnetic radiation and matter, and electromagnetic radiation is basically, or you can say it's a traveling wave of orthogonal electric and magnetic fields, and the amplitudes are varying in time, and of course both electric and magnetic field, which are mutually perpendicular to each other, are also perpendicular to the direction of propagation, and the propagation of the wave can be described by the wave equation, which basically it's derivable from Maxwell's equation. So the wave is carrying information about the source that generates it. Now, since we have been talking about separating a signal into its constituents, can you think of a simplest physical system that comes to your mind? White light, right? Suppose white light is incident on a prism, it separates it into its constituent colors. And so we can use it as a tool for examining the spectrum of different light sources. And it basically disperses the light by changing its direction of propagation proportional to the frequency. Now, sunlight is spread into an almost uniformly intense visible spectrum from violet to red. In a way, what we are doing here is that we are taking an electromagnetic wave, then using a dispersing element like prism, or in some cases it can also be a grating, and we are resolving a time varying wave into its constituent frequencies or colors. And these are independent of what form the dispersing instrument takes. So, whether it is a prism, whether it is a grating, the dispersion is not going to change. It is going to be dispersed in the same wavelengths, which basically determine frequencies. So, I hope you are able to get some idea about the Fourier decomposition of the waves. Here's an original wave, the amplitude versus time function is there, and it is getting transformed into an amplitude versus frequency spectrum. Now let's go back to the initial example of sound wave. Imagine that you have taken two different tuning forks and they're tuned to different frequencies, say 300 hertz and 600 hertz, and you are striking them simultaneously. What you will hear is the two frequencies making up the wave. So here your ear is performing a Fourier transform. So this is just some basic idea. In the next episode, we'll speak in more detail about how it is related to spectroscopy. Thank you.